Okay, guys, I'll be honest, I don't know how great this is going to be this time because the program I used to record the screen keeps messing up and it just deleted this entire video. But thankfully, this one's not as long as the previous one about conditional statements, which never seem apparently to upload, and neither is the next one. So it's a little less bad. But anyway, we want to talk about inductive and deductive reasoning, which is two types of reasoning. Here are some examples of inductive reasoning. Mary tried to sharpen 3 pencils. The pencil points kept breaking in the sharpener, so Mary concluded the sharpener was broken. All the students in Henry's geometry class are blonde. Susie is in another geometry class. Henry concludes that all the students in Susie's geometry class are also blonde. For the first 3 weeks of school, you had a geometry test on Friday. You conclude that your next geometry test will be on Friday. And let's look at examples of deductive reasoning. The sum of the angle measures of a triangle is 180 degrees. 2 angles of a triangle measure 40 and 60 degrees, so Juan concludes that the third angle measures 80 degrees. A detective learns that his main suspect was in jail on the day of the crime. He concludes that the suspect is innocent. In most schools, students must take biology before they take chemistry. Sam is in chemistry, so Marcia concludes that he has taken biology. Okay, so let's look back at the inductive reasoning thought process. So the one where Mary tried to sharpen the pencils, you might make a very similar conclusion. If you had 3 of them break, it's possible there's something up with your pencils, but it seems like the most likely answer is that the sharpener is broken. As far as Henry's geometry class, it's pretty weird that he has such a geometry class, and it seems horribly unlikely that that's true about Susie. So his example of inductive reasoning is not very sound thought. The one from the school, you're basically assuming that you know what the teacher's going to do because of what the teacher's done for the first 3 weeks. It's possible you're correct. It's possible that the first 3 weeks of school is sort of this pre-testing stage, so she knows where her students are, or so that he does. So it's not a great conclusion, it's a decent guess. If we look at deductive reasoning, well, the first one is definite fact, right? Any triangle is 180 degrees, so if 2 of them are 40 and 60, the other one is 80. The one about the detective, it seems pretty sure that the guy is innocent. There are some things that might have occurred. It may be that he had someone else do the crime. It may be that he did it early in the morning before he got in jail, but as far as what we can tell. But there's a pretty reasonable chance that he's innocent. And the one in the schools, if they were in a school that goes in a different order, like ours, and then they transferred to Marcia's school, then they might be in chemistry having not had biology. So it's not a certain conclusion, but it's likely. So in these 3, we have 1 is a certainty and 2 are very likely, which when we look back at the previous slide, this one seems very likely. These 2 aren't. So the best situation we got from inductive reasoning is basically as likely as the worst things we got from deductive reasoning. For which reason, in math, we mostly use deductive reasoning. There are methods to using inductive reasoning where they do produce factual arguments. Those are called principles of mathematical induction, which we may talk about next year in a brown bag lecture. But I mentioned in the previous video how scientists have to kind of take assumptions based on what they see. So they can observe and then they make theories, hypotheses based on what they've observed. And then oftentimes it happens that a year later, 100 years later, whenever, that they discover that the assumption wasn't true. And then in math, what we do is just say, well, if it's true, and never state outright that anything is true, except for conclusions following hypotheses. So that's the difference there. So scientists will have to almost exclusively use inductive reasoning because they have to start with what they observe. And mathematicians will almost entirely use deductive reasoning because they get to start with some kind of basic assumptions that don't necessarily have to be true. So the difference between the two words is with inductive reasoning, you start with something small and then you use it to make judgments about something bigger. And so maybe you notice a pattern, you assume the pattern will continue. With deductive reasoning, you start from the big and go to the small. So on the previous page here, Mary started with these 3 pencils and assumed something about every pencil ever. She assumes the sharpener's just broken. You take the first 3 weeks of school, you make an assumption about the next week. You observe a pattern. All the students in Henry's class are blonde. He starts from his class and he makes an assumption about all geometry classes. With this one, here's a fact about every triangle, and then Juan applies it to his specific triangle. This one, the detective takes the fact that the guy was in jail on that day and goes down to assuming he didn't do a single other thing on that day. In this one, we start with the thing about most schools, most students, and reduce it to a question about Sam, one person. So we want to decide which these things are. So number 4, Mark sees 4 people walk into a building. Each person leaves with a small bag of food. He concludes there's a restaurant in the building. So he's seen 4 people walk in. He's starting with a small set of people, and each of them leaves with a small bag of food, which they could have gotten from a friend, but he assumes there's a restaurant. So he's using inductive reasoning. It's reasonably likely, depending on the building, but it's inductive reasoning. Susan arrives at a traffic light, which is red. She uses a rule she learned in her driver's education handbook and stops. So the driver's education handbook tells you rules about all the traffic lights, and she's applying it to a single traffic light and deciding to stop. So that is deductive reasoning. Chris rides the bus to school. The trip takes 25 minutes. The next day, 24 minutes. The next day, 23 minutes. And the next day, 22 minutes. Or the next day, he assumes it will take 22 minutes. So he's noticed a pattern, 25, 24, 23. He assumes the next day is 22. So that is inductive reasoning. Started with a pattern, made an assumption about the next day and the next day and the next day. And it's, of course, not at all possible to follow that pattern because you'd end up eventually having to be there before you left. On Saturday morning, Brenda wakes up and notices that it is raining outside. The next Saturday, it rains again. So Brenda concludes that it will rain every Saturday. So she's noticed a pattern. It's raining Saturday, it's raining Saturday. Oh, every Saturday forever it's going to rain. This is, of course, also very false and also inductive reasoning. So we had inductive, deductive, inductive, inductive. And in this case, the inductive only led us to something reasonable once. Okay, so now we're going to look at some things that you have dealt with many, many times before, which is solving equations. And going back to the thing I said about in math that we say if such and so is true, then such and so is true. We have these things that we call axioms in math. So the things that you consider to be facts actually are either axioms or theorems proven by using the axioms and deductive reasoning, or principles of mathematical induction. But there are things that we say, okay, this seems pretty obviously true, so we're just going to go ahead and assume this, and if any of those axioms turn out to be false, then math all falls apart, but they seem pretty soundly true. So they work when we try to model real life situations. So some of those things are, I can add the same thing to two sides of an equal sign and it's still equal. Well, if an equal sign's a scale, the middle of a scale, which it is, then that's true in life. If you add the same amount of weight to either side of the scale, if it was balanced before, it's balanced now. Same thing with subtraction, division, multiplication. The distributive property just says I can apply distribution on one side and it still stays equal. The transitive property is if A equals B and B equals C, then A also equals C. So if I'm equal to two different people, then those people are equal to each other. And the substitution property says if two things are equal, then I can substitute them. So if I have that x equals y and x plus y equals 8, then I can make it x plus x or y plus y because they're the same guys, so I can plug them in for each other. And then the reflexive property says everybody's equal to themselves. A equals A, 2 equals 2, a tree equals a tree, assuming it's a specific tree. That's the reflexive property. So what we're going to do is start looking at something that's kind of what you've probably heard about proofs in geometry. This is an example. So we're just going to do steps that you've always done and then explain why we're allowed to do it based on some mathematical axioms. So the first thing you would do if you saw this, I feel certain, is to write 4x equals 20. You'd subtract that 5 first. So the fact that I'm allowed to subtract is the subtraction property of equality. And then you divide by 4 and say, well, x is 5. And that would be using the division property of equality. And then when you have x over 3, you would multiply by 3, and that's multiplying by 3 on both sides is the multiplication property of equality. This, if you'll recall, is called distributing. 3 times 2x minus 7. So you multiply the 3 times both of these, and that's distributing. So this is the distributive property of equality. Then we've added the 21. So addition property of equality. And then we divided by 6. So division property of equality. Down here we have x plus z is 5 and z is 1. So we put the 1 in where the z was for the next step, and that's just substitution. If r equals q and q equals s, then r equals s. That's a form of substitution by putting r, well, double substitution, I guess, putting q in for r and then s in for q, they're the same. But that's really just straightforwardly the transitive property. And then if a line segment is equal to itself, congruent to itself, that's reflexive. So this brings us to validity. So I'm going to pause and attempt to upload this one before it gets destroyed, and then I'll come back after a while.